So we can now start with the first speaker. There you go. So we can start with the first session of VMIL 2023. The first talk will be given by Duncan Lowther from University of Glasgow, and the talk is titled CHERI, Performance Enhancement for a Bytecode Interpreter.
Thank you. So I'm pleased to present this work, which Dejice and Jeremy sitting there, were also a part of. So I present on all our behalf. We have sort of three main contributions I'd like to talk about here. The first is our approach to the performance optimization of a CHERI based runtime. The second is a particular experience of the current profiling infrastructure on CHERI systems. And the third is an important observation about performance of CHERI systems in general. So first, what is CHERI or Morello? So CHERI itself stands for Capability Hardware Enhanced Risk Instructions. It's a set of instruction set extensions that allow certain spatial memory safety guarantees to be made in hardware. You can use it two ways, with a hybrid ABI that allows you to use mostly capability oblivious code that uses an implicit capability register to sort of make everything sound under the CHERI framework. And the second, the pure cap ABI, exposes the full features and the full protections, and that's the one we target because we're aiming here to maximize the benefits of security. Morello is a prototype architecture that implements the CHERI extensions on top of the ARM 8.2a instruction set. Specifically AArch64, we don't deal with AArch32. Morello capabilities, so capabilities in general are fat pointers that contain privilege information as well. So anytime you make a memory access, you need to have a capability authorizing that access. A capability will have its address, that's just your standard pointer. You can do normal pointer arithmetic on it. The other bits of it are a bit more interesting. You've got bounds, which are the region of addresses over which the capability is valid. If you try to use a capability to authorize an access out with the bounds, it will fail with an architectural trap. You've got permission flags, 18 of them. These include, read, write, execute, as well as some more specialized permissions like being able to read and write other capabilities. You've got an object type field that I'll explain a bit when I come to sealing. And you've got a provenance tag. This is possibly the most important thing. You've got a 1-bit tag stored out of band, so you can't access it directly with any sort of memory instruction that allows you to distinguish a true capability from just a sequence of bytes. So this guarantees that capabilities are properly derived from other capabilities. If you use an invalid chain of derivations to create a capability, the tag will be cleared and you won't be able to use it to authorize anything. Derivations of capabilities are monotonic in bounds and permissions. You cannot widen the bounds or increase the permissions. Permissions are dealt with a bitwise and bounds will throw a trap if you try to widen them. The object type field allows you to seal capabilities to prevent modification until they become unsealed. So this is a bit of a special thing. The most important kind of sealed capabilities are sentries, which are a way of protecting function pointers so that you can't change the the address with you can jump to the entry point, but you can't jump to an arbitrary point in the function, which foils return-oriented programming attacks, and you can't read the actual code of the function either without jumping to it. So it's also important to note we have single source provenance. Each capability has to be derived from exactly one other capability. So you can't merge two adjacent capabilities together. That's not allowed in this system. Some implications here. The size of our pointers is longer than the size of our integer words. If you cast a pointer through just a long or other integer type and back to a pointer, you will lose the provenance, you will lose the metadata and the capability tag, and you won't be able to actually use it to dereference. If you cast through the uint pointer t type, that will preserve provenance because that's a type specifically defined to allow you to preserve pointers as you cast them through an integer. A related thing though, because the uint pointer t type then has to actually hold the entire capability, adding to int pointer t types is ambiguous because, like I said before, you can only derive a capability from one other capability. And so it doesn't know whether you're adding the address of the second to the first capability or the address of the first to the second capability. So the compiler will complain about that. You have to explicitly throw away the provenance of one of your operands before you can use these binary operators. Next, the maximum representable value for a uint pointer is not what one would expect based on its size of, because the top 64 bits of the uint pointer are reserved for the capability metadata. So the representable range is only that of your 64-bit integer, despite being 128 bits in width in memory. So those are a bunch of bad things, or things that have to be worked around. The last thing is very important and is the big positive, and that's that many undefined behaviors in C that would ordinarily might corrupt arbitrary data or result in leaks of various kinds, or maybe a seg fault, but you can't guarantee that, instead become a predictable capability protection fault. That is guaranteed to be thrown if you make an access that's invalid under CHERI. So this is an important protection. So in prior work, we ported the MicroPython interpreter to PureCap, and MicroPython is a bare bones Python interpreter designed mainly for embedded systems, so it's optimized for code size, but it has desktop ports as well. And in yesterday's talk at MPLR, I detailed how we ported the sort of biggest variant of MicroPython to the CHERI-based Arm Morello and under the PureCap ABI. And there's a DOI there for anyone who is interested. So next, we get onto the subject of this talk, which is the benchmarks and the performance enhancement that we did on this. So anytime we talk about performance, we've got to specify what benchmarks we're using. So there are 11 benchmarks in the performance bench suite built into MicroPython, so we decided to use those for consistency with MicroPython. I also got to detail our metrics. So of course we track total time because that's the sort of the important execution overhead that we want to see. We also tracked RSS because the idea of having all pointers twice as large, we want to see what the impact in real terms on memory is. We also tracked instructions retired and cache misses in order to help diagnose the source of execution overheads. And lastly, it's important to notice that all the figures that we'll use henceforth will be normalized, so they'll be represented as the ratio of the PureCap build value to the hybrid build value. The PureCap and hybrid builds are run on the same machine, so they should be comparable from a hardware standpoint. So before any optimizations, we had this scary headline figure of 137 times overhead on the Van Kuch benchmark. And you can see a similarly upsetting overhead in Queens. Both of these, you'll note, also very high instruction retires. So the CPU is clearly very busy in these. So our symptoms, both our benchmarks that were worst off, involved repetitive list slicing operations, which is interesting. And list slicing in Python requires actually allocating and then quickly deallocating a whole bunch of heap objects. Using PMC stat, which is the BSD sort of equivalent of perf, and sampling every 2 to 16 instructions, we found that 99.3% of our samples landed in the allocator. So that quickly tells us the sort of general situation. As a side note, it was difficult to use PMC stat because the built-in PMC stat way of translating raw addresses into what symbols they relate to doesn't actually work on PureCap. So I had to write a bit of an external script to be translating them for me from an extracted symbol table. The vast majority of these samples within GCalloc were in a loop that searches for a contiguous set of free blocks long enough to hold the allocation. And we also noted in the statistics when we told it to dump GC data that we had far fewer one-block allocations on PureCap than on Hybrid. So Hybrid had a few thousand one-block allocations, far more than any other block count. PureCap had only 12 of them, and there were far more two-block allocations. So you might see where this is going. The doubling of pointer sizes has caused, with no change in the block size, has caused allocations that would ordinarily be smaller to take up more blocks, to take up 2-3 blocks. And because of that, we're dealing with memory fragmentation. It turns out the MicroPython allocator, it's designed to run very lean in its sort of home state. But if you don't have a lot of one-block allocations, it will quickly become very fragmented and have huge performance hits based on that. So the fix here was to change the default block size from being based on the size of an integer, which is of course the same on Hybrid and PureCap, despite the pointers doubling, to one based on the pointer size. MP-object-T is the sort of standard type for MicroPython objects that is a low-bit tagged union of either a pointer or an unboxed integer or intern string identifier. So after doing that fix, you'll notice we no longer have any 3-digit overheads, which is nice. In fact, the benchmark that we were worrying about earlier is down to 1.7 times. It's no longer our biggest culprit. We now have to worry about Pystone, which has nearly a 4 times overhead. And the fix turned out to be actually quite similar. So if we look at flame graphs, which basically show the samples over time from the PMC stat, so you can see the entire stack trace. And it's not linear time. It's not like it goes right to left. They're merged, so you can see how much of the time is taken up in each function. And you'll notice I've outlined in red the GCalloc calls. So again, while it's not 99% now, we're winding up with a significant amount more time in the allocator on PureCap than on Hybrid. It barely visible on Hybrid, but PureCap is quite significant. So Also, the most expensive calls to GCalloc came from this funBC call. So we examined that function in particular. We also instrumented the GC, and it turns out there are 200 times as many of those free block search loops on PureCap as on hybrid. So clearly, again, stalling there. We also noticed that there were thousands of 3 and 4 block allocations that appeared in PureCap that didn't appear in hybrid. But unlike the previous issue, these weren't allocations that had previously been smaller on hybrid and are larger on PureCap. They didn't exist at all on PureCap. So this was a bit confusing until we realized that the funBC call, the only place that function directly calls the allocator is when it wants to spill a call frame to the heap. So only, by default, only frames no more than 16 integer words in size get stored on the stack. Anything else gets allocated on the heap. And so, again, because this is based on an integer word, when we switch to PureCap and the size of the call frame has a lot of pointers in it, so that's going to increase significantly while the maximum size on stack hasn't changed. So we're going to wind up with a lot more spills. And in particular, the 3 and 4 bytes, 3 and 4 block allocations correspond to the exact set of sizes that can be allocated on stack in hybrid, but once you double them, wind up being heap allocated. So the solution here was to base the threshold for spilling on pointer size as well. So you'll notice in both of these two things, the issue is fix an assumption about pointer size being equal to integer size that was assumed in optimization earlier, and that allows the optimizations to sort of be compatible. After this, you'll notice we dropped by about 1/4 there, so we're at 2.8 times. Still too high, but you'll notice that we're getting more and more sort of not CPU busy, or not instructions retired at least. So we're getting to the point where it's going to be a bit more difficult to optimize because we're not just spinning. At this point, the side-by-side flame graphs didn't tell us much because they were too similar looking. There wasn't enough visible difference. So we use this sort of difference flame graph where the color indicates the overhead of PureCap relative to hybrid. More red is more overhead. And you can see here that now the execute bytecode method there it accounts for both of the two reddest areas. So that's our VM loop. That interprets the bytecodes that we've compiled down to. It uses a table of computed gotos to make a very tight loop. And for some bytecodes, an iteration of this loop, a processing of the bytecode, including the goto, is 11 instructions. So any sort of slowdown there winds up getting magnified significantly. What we found out that this actually was inadequate LLVM optimization. So there are several places where LLVM, when compiling on PureCap, knows that it can optimize things down, and that when inspecting disassembly, know that these instructions are superfluous. You could just use one instruction where you used 3. But because the LLVM PureCap compiler doesn't yet know that is true for capability-based things, it's generated longer binary code than it needs to. So a couple examples. Whenever we had to load a small constant uint pointer, which it appears as capability, it was compiled down to 2 instructions to load that rather than 1. When we wanted to cast an integer without provenance to a uint pointer t, that took 2 instructions, where by default, if you've moved untagged integer into a register, it will clear all the top, all the capability bits, and so you don't actually need any instructions to cast whatsoever. And then it took 3 instructions rather than just 1 to compare a uint pointer t against a constant. Now, compares of capabilities are done only on the addresses, so you could just do a single instruction for an address compare, but instead it loads that constant as a uint pointer t using 2 instructions and then performs a compare on the integer parts, which is just unnecessary. So it wasn't, fixing this directly would have required delving into the LLVM backend and was a bit out of scope for this project. But what we did to prove that this was a real overhead was we went in and patched the binary so that we could see the changes of at least some of these optimizations. We didn't patch every, just a few patches in the execute bytecode. And you can see that created, another drop by 1/3 in normalized total time. So this is after our 3 sort of quick optimizations. Not very sophisticated at all at this point. And we've now got everything down to between 1.5 and 2 times execution with a geomean of 1.7. You also notice instructions retired is quite low there too. That winds up at a geomean of 16% overhead. And most of the sort of higher bars are the caches. So what do we take away from all this? First off, the PureCap CHERI port can have a significantly different performance than the legacy code if it's just naively ported. Anytime you're porting CHERI code, there's been a lot of focus on needing to fix assumptions made around functional requirements of the code, but the assumptions made when creating non-functional requirements, equally important. Porting efforts should pay attention to assumptions made when optimizing the code, not just when making it correct. Otherwise, you wind up with these 100 times overheads that no one likes. The good news is it's actually fairly quick to fix these sort of assumptions in a lot of cases, because it'll be, one define or one, constant somewhere that needs to be tweaked, and then suddenly everything's better. The last thing is that the headline figure, 70% overhead, shouldn't be discouraging. So we've got further optimizations potentially available at the source level. We haven't looked into, for instance, removing redundant bounds checks, because CHERI does hardware bounds checks, so their software bounds checks can probably be removed. Using the tags built into the capabilities to make more efficient the distinction between a pointer to an object structure or an unboxed value. Various things like this that can be changed at the source level. Second is that the Clang LLVM optimizations are improving as the toolchain for PureCap matures. So it is fairly recent, and the optimizations are being worked on. And the last is that the hardware is going to improve. So the report out of Cambridge that's fairly recent on the performance of Morello suggests there will be significant future improvement. There are currently bottlenecks, for instance, in the branch predictor if you're using branch to capability instructions. And well, guess what? The tight loop that I was talking about with a computed goto, on PureCap, that winds up being a branch to capability. So given that we only saw a 16% overhead in instructions retired here, it seems fairly likely that improved hardware can reduce the overhead in execution time significantly, which agrees with what Cambridge was saying about this. So that's all from me, and yeah.
So thank you very much for your talk. Is there any question?
So you sort of alluded to it. Can you use the object tags as user code to indicate like type tagging in a dynamic language system?
Yeah, so you're talking about the capability tags, right?
Yeah.
Yeah, so they have the architectural duty, right, of distinguishing a valid capability from something that's not a capability. So you can use it if you've got something that can either be a pointer or not a pointer. You can distinguish based on that object tag. It doesn't get you more fine-grained than that, but it can get you that. The one thing you do have to worry about if you're doing that is if you do certain invalid manipulations on a capability, it will clear the tag on the capability. So you've got to be careful that you're not having a situation where a capability with a cleared tag winds up getting misinterpreted as an object of a different type and causing weird behavior that you don't expect.
And that seems good, but...
Any other question?
So have you applied source code optimization to MicroPython? Because at the end you mentioned that the advantage of using Morello is you can optimize check type tag checking and etc. So have you
Yeah, so I mean, that's something we definitely plan to do going forward. At this point, we were really just looking at the way you can bring the overhead that you've gotten by porting it down. So trying to sort of mitigate the sources of overhead rather than direct improvements based on what we have now. But that is definitely sort of the next step. And like I said, that is likely a fruitful area.
Any more questions?
Do you know where the rest of the 16% is coming from? Is that mostly constructing capabilities, or is it additional wider compares that you need, or?
Yeah, so I mean, it comes from a few places. You've got situations when you take the address of something on the stack, for instance, the compiler automatically inserts instructions to give it proper bounds, so that you're not, if you then pass that to somewhere else, you're not allowing access to the entire stack. Similarly, in the heap allocator, there will be a place that narrows the bounds before it returns, and then in a reallocate free, a place that rederives the wider bounds from an existing sort of whole heap capability that it maintains. So you've got a few places where you've got to add extra code just innately. It probably could be brought down further, to be honest. This isn't a comprehensive treatise on all possible sources of overhead. This is just showing sort of the biggest ones that can just be knocked out very simply if you know what you're looking for.
Thanks.
I think we have time for another question, if there is any. Yeah, maybe a quick one.
So what is instructions retired? I'm not familiar with the term. Could you explain it in very short?
Okay, so yeah, so it's just the number of instructions that the CPU has actually completed for working on the benchmark. So, just count each time an instruction is executed and fully completes. That retired means, it's not speculatively executed or partially complete. It actually completes fully. Then you increment instructions retired.
Thank you very much for your talk.